A senhora tá boa
Não.
de enxergar? Essa outra pequenininha aí.
É.
No começo.
Vou deixar aqui, tá, Chico? Hoje o Líbio chegou lá e não saía de lá, e eu querendo organizar as coisas. Mas isso aí, Geraldo, vou bater.
Acho que pode acender a luz só um pouquinho. So good afternoon, everyone. It's a great pleasure to receive all of you over here, the guys which are in our audience, online and in presence. Thanks so much for your attention, and we have a great honor to receive here at the Santa Catarina State University Professor Robert Gilmore Pontius, Jr. from Clark University. Please, Professor, get a seat. And also, I would like to introduce you our provost, Professor Letícia Sequinato. She's a provost from UDESC in research and post-graduation area. Also, we are going to have two moderators. One is Professor Carlos Vieira. He is a student, our student here in UDESC, but also is a professor in another university. And last but not least, Professor Lisenberg, which is also our professor of remote sensing here at UDESC. Please, Professor, take a seat. Thanks so much for all of you in this afternoon. I'm going to be quite quickly. I'm going to begin to read just a bit of Professor Pontius' CV, because it's a long and huge CV, a notorious guy in the geoscience area, which everyone knows in advance. So, Professor Gilmore creates quantitative methods that contribute to geographic information science, remote science, and statistics. Professor Pontius is an applied statistician and environmental scientist with expertise in GIS, ecological modeling, and land change science. Also have been contributing quite a lot with Brazil mapping in a program called Mapbiomas, and it's a great honor to receive you over here. Also, I'm going to present the CV of our two moderators, which is Professor Carlos Antônio Oliveira Vieira. He is a surveying engineer and studied in England, where completed his PhD in geophysical geography at the University of Nottingham. His thesis is entitled Accuracy of Remote Sensing Classification of Agricultural Crops, a Comparative Study. In 2001, he received the award for the best doctoral thesis offered by Remote Sensing Society. In August 2005 to 2006, he completed his postdoctorate fellowship in geomatics at the University of Melbourne, Australia, and he is currently full professor at UFSC in the Department of Geology, but also a student of administration, public, here at UDESC University. Our second moderator is Professor Veraldo Lisenberg. He is a forest engineer and got his PhD in environmental geoscience at Technische Universität Bergen-Akademie, Freiburg, Germany. His PhD thesis is entitled Characterizing Tropical Secondary Forest Environments Using Multiple Types of Remote Sensing Data in 2013. His post-PhD was at Unicamp between 2013-14. Professor Lisenberg is a teaching professor for UDESC in forest departments. Well, right now I would like to invite our provost, Professor Letícia Sequinato. She is right now giving us a welcoming for this lecture. And please, Professor, she can speak in Portuguese or in English, whatever. And it's just a warm welcoming to Professor Pontius and all of us. Please.
Thank you. Em português? Ok. Uma boa tarde a todos e a todas. Um cumprimento bastante especial aos colegas que estão já aqui à frente, que já vou anunciá-los aqui no meu breve discurso de abertura. Boa tarde especial à plateia que está presente aqui, inclusive equipe da nossa Pró-Reitoria de Pesquisa e Pós-Graduação da nossa instituição que está aqui. Uma boa tarde a todos que nos assistem online pelo YouTube. Sabemos que temos aproximadamente umas 100 pessoas online. Sejam muito bem-vindos e façam um ótimo proveito desta grandiosa palestra. Nossa saudação bastante especial ao professor Robert Pontius, que está aqui presente com a gente hoje, da Clark University. O professor Pontius tem grande destaque na ciência geoespacial e ambiental, conforme também já colocado anteriormente, cujo trabalho tem impactado positivamente a compreensão das mudanças na cobertura e uso da terra, bem como a aplicação de técnicas de sensoriamento remoto para conservação e gestão ambiental. É uma grande honra tê-lo conosco, professor Pontius, para compartilhar seu conhecimento e insights durante a palestra que tratará do tema já abordado. O professor Pontius, por meio de sua palestra, irá tratar então desse importantíssimo tema, não somente para Santa Catarina e Brasil, mas é um tema importantíssimo para o mundo todo, que envolve as mudanças na cobertura e uso da terra. Agradecemos por compartilhar de seu conhecimento. O professor Pontius é conhecido por seu trabalho na colaboração com o Mapbiomas, uma iniciativa que visa mapear e monitorar a cobertura e o uso da terra no Brasil. Sua contribuição para o projeto tem sido essencial para melhorar a qualidade dos mapas gerados e permitir uma avaliação mais precisa das mudanças do ambiente. Um tema tão importante na atualidade. Gostaríamos de estender nossos sinceros agradecimentos ao Geolab, que é o laboratório de geoprocessamento desta universidade, ao coordenador do laboratório, professor Francisco Henrique Oliveira, que também está trazendo essa importante palestra no dia de hoje. Um agradecimento especial também a todos os colaboradores do laboratório, professor Francisco, por organizar e possibilitar este evento bastante enriquecedor. Agradecemos ainda os professores moderadores que já foram apresentados, professor Veraldo, que é nosso colega aqui da instituição, que pertence ao CAV, que é o Centro de Ciências Agroveterinárias da UDESC, que fica em Lages, e ao professor Carlos Vieira, que é um professor da UFSC, mas também é aluno desta instituição no curso de Administração Pública. Muito obrigada também, moderadores. Também gostaríamos de expressar nossa gratidão ao Programa de Pós-Graduação em Planejamento Territorial e Desenvolvimento Socioambiental e ao Departamento de Geografia por apoiarem essa iniciativa e promoverem o aprendizado e o avanço do conhecimento em suas áreas. E também parabéns à FAED por estar recebendo este importante evento. E, claro, um agradecimento especial à parceria entre a UDESC, essa nossa instituição, e a equipe do Mapbiomas. Nosso muito obrigada. Tornou possível ainda essa parceria a vinda do professor Pontius até este evento na data de hoje, que nos oportuniza aprender com um especialista tão renomado internacionalmente. Estamos entusiasmados com a parceria entre a UDESC e a Geoscience in the Remote Sensing Society, por meio da qual muitos pesquisadores e interessados no tema estão assistindo remotamente pelo canal do Geolab no YouTube. Agradecemos a todos os participantes por se juntarem a este evento bastante significativo. Que esta palestra seja inspiradora a todos nós e muito frutífera. E não temos dúvida que será, proporcionando novos insights e conhecimentos para todos os presentes. Desejamos a todos um evento produtivo e enriquecedor. Novamente, fica o meu muito obrigada, em nome também da instituição, do magnífico reitor, professor Gilmar Bareta, desta pró-reitora, professora Letícia, de toda a equipe da nossa pró-reitoria, que também faz com que ações como essas se tornem possíveis. Muito obrigada, Pontius, professor Veraldo, professor Vieira. Tenhamos todos um excelente evento, sejam todos muito bem-vindos. Muito obrigada.
Obrigada, professora Letícia, pela apresentação. Thank you so much, Professor Letícia, for the warm welcoming. Now, I would like to invite Professor Pontius to begin your lecture. Please, it's a great honor. The word is yours.
Thank you very much. It's the great honor and privilege is mine. I thank you so much, and Madam Provost and distinguished professors, thank you for inviting me. And I'll inform everyone in the room, we have more than 100 people registered online that are watching, and they will be able to see two screens, the PowerPoint file, and also a video. Unfortunately, they will not be able to see the thousands of other people in the audience. Yeah, sure. No, please do. And I'd like to thank my funding agencies, most recently NASA, who generously awarded my team a 3-year grant. And so we will be studying adaptation to climate change in the Cerrado, specifically using irrigation. So agriculture will be an extremely important part of this research. And we are actively looking for graduate students to come to Clark University and to spend time doing research on this. So if you are a master's or bachelor's student and you want to go to the United States for a doctorate, well, please speak to me afterwards. Or you can send me an email address. Here's my email address here, and my website. Also, much of this work has been funded by the United States Long-Term Ecological Research Network, and this is my second year in Brazil. Last year I was here for 6 weeks. This summer, this year, I'm here for 10 weeks by funding of the Fulbright organization. Well, here are the, let me first start out with my name. This is my full name. It was not my choice. I thought I had a complicated name until I met Brazilians. But since I was born, people have called me by the first half of my middle name, Gil. My father has the same last name, thus the junior. You will see the literature under my name. That's why most people in Brazil just call me Pontius, and that's fine with me. And there we go. So here are the 4 main points of this. I'll speak for about an hour, and then we'll have discussion. When I say we, I mean my students and I, we created novel methods to compare the Mapbiomas time series of land cover change to reference data that derive from visual interpretation. Mapbiomas data show more alternation change than the reference data show. And as the presentation goes along, I'll define what I mean by alternation change. Uncertainty in the reference data is 30 times larger than the annual change in the Mapbiomas data, and will show novel methods to analyze change in soybean cultivation in western Bahia. So these are the four main messages that you should be looking for during the presentation. This is the last slide that I'll show. So next time you see this slide, that's your cue to applaud. Here we go. I have to point that, not the screen. Right. Okay. I am at heart a mathematician. My master's degree is in statistics, and I love maps. So that's why I'm a geography professor specializing in GIS and land change science. And I say I am a mathematician and statistician, but I hate looking at tables of numbers. The problem with numbers is that 8 is 4 times larger than the digit 2, but 8 and 2 take up the same space when you write them. Very frustrating for people like me. I think 8 should be 4 times larger than 2. I need to see things graphically. One of my favorite graphics that has inspired nearly all of my work is this same graphic that we all saw in, middle school? When you were maybe 13 years old in math class, you saw a Venn diagram. So the Venn diagram has a border of the universe. This is the boundary of the system. And a Venn diagram has 2 circles in it. But my circles are more special than the circles that you've seen in all of the math books that you've ever seen. My circles have different sizes. Ooh, big innovation here. Well, why did I draw them different sizes? Well, my math teacher says, well, they might look the same size, but you don't have a mathematical proof that they really are the same size, so you shouldn't assume they are. Well, then why did she draw them the same size? Okay? I drew them different sizes for an extremely specific reason. Because when we use the analogy of the Venn diagram to apply to the methods that I'll be talking about, those circles are not necessarily the same size. So, what if we assume that each circle represents a particular land cover class? Oh, we pick your favorite one. Soybeans. It's a favorite one for some people in the room. Okay, so we might have soy here in the red circle at time 1 and non-soy outside of the red circle. And then we might have presence of soy at time 2 in the blue circle and not soy at time 2 outside of the blue circle. Where they intersect, that is a persistence of that class. And so with those those 2 circles can overlap, and we'll have 4 parts to the, there we go. So we have 4 parts. The intersection is stable presence of the class. If it was present at the start time, at time 1, and it's not present at time 2, it's a loss. If it's present at time 2 and not at time 1, it's a gain. And if it's outside of both of the circles, then it's stable absence. Okay? If you can understand this diagram, you can understand 90% of the methods that I'll be presenting. But notice, since I have the circles the same size, what you see here is the gain is larger than the loss. And so If the gain is a different size than the loss, that's a kind of difference I call a quantity difference. So a quantity change is the absolute value of the gain minus the loss. But the total change is the gain plus the loss. So there's another component of change that's called allocation change, and that's the total difference minus the quantity difference. So we could take the total difference, gain plus the loss, that's the total difference, and split that into two parts, a quantity difference and an allocation difference. And I will return to this concept again and again during this presentation to look at the total change and then split it into separate components, and where each of those components has a very specific interpretation. Now, so that concept relates also, I just showed how that concept relates to measuring temporal change. Now I will show how this same concept relates to what some people call accuracy assessment. And at first I liked that phrase, then I said, no, I don't like that phrase. Because people are focusing on accuracy, meaning the agreement. And I realized people don't learn when they report the agreement. They just hear the word agreement and they say, oh, God, that's good, and they move along. Your opportunity for learning is where the disagreement is. So then for a few years, I was using the word error assessment, E-R-R-O-R, error assessment. You're focusing on the disagreement, because if you understand the disagreement, that's your opportunity to improve. But recently, I've changed my term to data quality assessment. Why? Because I do not like the word error. Because error implies one data set is true and the other is wrong somehow. But we will see examples where it's very, very difficult to create data that you consider true. So we can use this concept to, if you do believe in truth, the word truth is helpful just to represent some data that you think has the best available accuracy that you can generate. You could think of the red circle having the presence of a class in the map that someone makes, that maybe a remote sensing agency makes. And then that remote sensing agency goes perhaps on the ground to see what's truly on the ground, or does some sort of visual assessment and determines that the class is really the blue circle. And so perhaps the class is pasture. And so again, you have a Venn diagram where the blue circle is larger than the red circle. But so you have 4 parts to the red Venn diagram, but now the 4 parts have different words. The intersection is called a hit. So that's when the class existed in truth and bam, the classification hit it. A miss is where the class existed in truth, but the map failed to have it. Map missed it. The false alarm is where the map says, watch out, there's pasture there, and you go, and in truth, there's not. And correct rejections. That's when both the map and the reference information, the truth information, says that there's absence of that class. So same concepts, but slightly different words for a different type of application. And again, you have the exact same concepts. The total error are the false alarms plus the misses. The quantity error is the absolute value of the false alarms minus the misses. And then the allocation error is that total error minus the quantity error. Now, for the big conceptual step. Did you see the transition from the previous slide where we had circles to now this slide. See, circles. Now, ooh, rectangles. Same concept, okay? You will not see those circles in journal articles. You will not see the rectangles in journal articles. But why did I put the rectangles? What you will see in journal articles and reports is rectangles, but they will be rectangles in this form. Okay? Much research gives this what's called a 2x2 matrix, where the rows are the classes in the map, the columns are the classes in that you consider the best available data that you have, and the shortcut word for that is truth. And so if your map says it's presence and the truth says it's presence, it's a hit. If the map says it's presence, but in truth it's not, it's a false alarm. If the map says it's absence and the truth says it's presence, it's a miss. And if they both say it's absence, it's a correct rejection. Some of the literature will give you these words: hit, false alarms, miss, and correct rejection. Most of the literature will give you those words. What's this? Oh, a true positive, a true false positive. You remember seeing those terms? You know, you get your COVID test back and it's a false positive, and you have to think, wait, positive is a bad thing. And then many people get very confused with those terms: true positive, false negative, etc. I found these words are much more helpful to communicate. So the journal articles will have this table that derive from, let's say you have 10 pixels here. P stands for presence, A stands for absence. If the map says it's present and the truth says it's present, then it's a hit, and it goes here. If the map says it's presence and the truth says it's absence, it's a false alarm, and they go here. If map says absence, truth says presence, you got misses, 3 misses there. And if both the map and the truth say absence, those are correct rejections. You got 4 there. So these add up to the 10 observations there. Well, I said I do not like looking at numbers and tables of numbers. That's why I took this one, that table, and made this graphic. So on this graphic, we've got the axis here going from 0 to 10. Why? Because there's 10 observations here. So this is the size of the spatial extent. What I have here are, I've drawn in 2 sets. The green, what's outlined here is the presence for Y, and that goes up to 4. So that's this 4 here. And here is the other set for the presence of X, and the width of that is 3, and that's the 3 there. Where those 2 sets intersect, those are the hits. Here on this side, on red, those are the false alarms, and everything in green is a miss. But notice that there's more misses than there are false alarms. And if there's a different size of misses than false alarms, then the larger one has a quantity component. So I wish people would present their data quality assessment in this form rather than this table, because that a graphic can just influence me much more. I can immediately see the results much better. Okay, well, how do these ideas relate to my collaboration with Mapbiomas? I'm now on the scientific advisory committee of Mapbiomas. My involvement with Mapbiomas has been getting deeper and deeper over the years. I've been involved with Mapbiomas, I don't know, about 5 years now. How many in the room have heard of Mapbiomas? Okay, it looks like about half, maybe more than half. Great. Well, on the, maybe for the people who have not heard, Mapbiomas is a nonprofit organization centered in Brazil, and they create what in my career is the best time series of land cover maps that I have ever seen. They have 30-meter resolution maps for all of Brazil, actually most of South America. They're now expanding into Indonesia. They have dozens of classes. They have every year going back to 1985. So it's petagrams of data. So it's not an option just to say, oh, I want to see the Mapbiomas data. It's petagrams. You have to think very carefully about how to look at it. And then you need to write a computer code to be able to visualize it that way. But Mapbiomas, you know, their audience is very important to them, and so they make the data available and some of the results on the first page of their website. And so Mapbiomas decided that this should be on the first page of the data platform. They have a map of Brazil for each color is a different land cover class. And then they have this graphic where the horizontal axis is time and each of the lines is a different land cover class. So the next slide is a zoom in of this particular graphic here. And so this is the years going from 1985 to 2021, and this is in million hectares, and each color of line is a different class. So naturally the green line is forest, we got yellow for agriculture, and on my computer it looked orange for pasture. Okay, so forest is decreasing, agriculture is increasing, and then levels off, pasture increases, and then it has a slight decrease. So what this graphic is showing is just the size, and that is a quantity change. And this graphic, in fact, according to one of my students, it's not even a time series analysis. Because he told me, well, look, they just analyze the size at each year and put the results close to each other. So they can analyze the size at 2003 without analyzing any other data point. Okay? They can compute the size for 1991 with ignoring all the other data points. And so in my student's criterion of a time series analysis, he doesn't even call this a time series analysis. In his view, a time series analysis would be where the result requires that you consider all the time points together. And so I'm on the scientific advisory committee of Mapbiomas to give them advice. And I'm looking at this and saying, this is the first graphic that they present. And it does not even meet the criterion of a time series analysis of my student. I'm thinking, is this really the best graphic to show? Because this graphic does not show the type of change that the Venn diagrams show. If you have, we know that forest is decreasing, but that decrease is a function of a large gross loss in some places, but even within the same year, forest is gaining in other places. And so if you have a one-year time interval where forest loses some places and gains others, it's as if the forest reallocated where it is. And this graphic doesn't show the allocation change at all. And when we started to analyze the data, we realized the allocation change is much larger than the quantity change. So if you see only this, it dramatically underestimates the size of change. Furthermore, some of that change happens at the same places year after year. Well, at the end of the presentation, I'll give an example of soybean cultivation. We analyzed the time series of soybean cultivation and looked at all the changes in western Bahia, and found that most of the changes were due to an alternation. And an alternation is a pairing of a gain and loss through time. So you can have the same places will gain, the gain maybe stay present and then lose, and then gain and lose, and gain and lose at the same places. So if you look at only the change in the quantity through time, oh, you might see a slight gain from the very start to the very end. But the amount of change might be a lot more. And so this graphic is showing only quantity change. It's not showing these other two types of change, of allocation change and alternation change. So in the presentation, I'll show you how to measure those other two types of change. Okay, the other thing that this graphic does not show is the data quality. Mapbiomas, I've remained with them for years because I'm very impressed with them. These are some of the most serious scientists I've encountered. They're well trained, they're well educated, they enjoy their job, they take it seriously, and they listen to their audience and they revise the data every year. And they're very concerned about data quality. And so they did a data quality assessment, and they estimated that their data are 88% correct. Does that change your opinion in how you interpret this graphic? Well, when I hear 88% correct, well, I think when most people hear 88% correct, they just hear some number that's sort of large and they hear the word correct. And as soon as they hear the word correct, their mind stops working. And they say, oh, okay, that sounds good. I'll look back at the graphic and I'll believe the graphic. But when I see 88% correct, what my mind says is that the data are 12% wrong. Now, if I told you the data are 12% wrong and then gave you this graphic, well, come on, take a look at forest. The entire drop in forest looks like less than 12%. So are you having more error in the maps than the variation that's shown on these lines? That might be a problem. But that 12% that's wrong, that's the total error. But this graphic is showing only the quantity differences. So it seems we should be thinking about only the quantity error. If I'm estimating forest and the amount of false alarms, if the size of false alarms is the same as the size as misses, then I've estimated the quantity of forest perfectly. I could even have 50% error and still estimate the quantity of forest perfectly. So what's really relevant here is the quantity error. And so Mapbiomas, read some of my literature. The calculations to separate the error into the two components are the most complicated mathematics is division. Okay. And so if you look at the quantity error, the data have only 3% quantity error. It's like, oh, well, maybe now I'll actually believe these results, because it looks like some of this quantity difference is larger than 3%. It looks like you're getting a larger observed temporal difference than you have error in the maps. So for every pattern in which you're interested, you need to think very carefully about what characteristic of the data quality is necessary for you to believe a particular pattern. And so it's a habit in remote sensing simply to report percent correct. And then in the papers that I've seen, it seems whatever percent correct they have, they claim victory. If they say it's greater than 85%, they say, we are greater than 85%. And they leave it at that. But very frequently do I see literature where they have aligned their metric of accuracy with their particular research goal. And so, in fact, I make a habit of going to professional conferences and asking people why they used the particular metric that they did. And I get answers like, that's what people in my profession do, or my professor told me to, or the software reports it, or I don't know. And I really respect those answers because they're remarkably honest answers. But when I've asked people, why did you use the metric that you did, I have never received the answer because this metric answers our research question. It's remarkable. People present a lot of metrics almost entirely out of habit. So let's take a look at what metrics would be relevant for the Mapbiomas time series. What we have here is on the time series axis, we have the height of the bar is the amount of change, and this is the change in this Amazonia biome, and that change is broken into various components. The blue part of the change is the quantity component. The red and yellow parts of the change are the allocation components. So what we see is there's much more allocation change than there is quantity change. So that graphic that has the lines, it's missing most of the change. So next. Furthermore, most of that change that we see here is from year to year is change that's happening at the same places. So that graphic did not show the alternation change. But what Mapbiomas wanted to do was to know the data quality. And so what they did, they contracted with these researchers in Guyana at Lapig, the Geoprocessing Center. And here is some of the team that creates the truth for Mapbiomas. Well, if you think what they create is the truth. Other people call this reference data. Okay, so these are the people who did the visual interpretation to create data to then compare to the Mapbiomas time series. In fact, these people are not the exact visual interpreters. But what they did at Lapig, they trained people in a few days, and I think these were mostly undergraduates. They trained them to do this visual interpretation, and then they put them in a room and had each of them look at each point and look at that point for all 37 years. And the number of points they had these people look at was 85,000. That's a lot of work. Imagine if that's your job. How many hours could your concentration really last? Looking after image for 85,000 points that were selected through this stratified random sampling design. They worked with an excellent statistician to think very carefully about the sampling design because it's a tremendous amount of work. If you do not have a cleverly designed stratified sampling design, you will waste a lot of the time of the effort of those. So they have 85,000 points here. They have it stratified in each of these rectangles. The black dots represents the points. And for each of those points, the visual interpreter would look at that point for each of the years. So imagine looking at this image and seeing what class that image is. They had 15 interpreters, 3 supervisors, because sometimes the interpreters disagreed. Each point they had 3 interpreters look at. And if the interpreters could not agree, then the interpreters would go to a supervisor. And like if all the 3 interpreters give a different class. If 2 interpreters give one class and 1 interpreter gives another, then it's a majority rule. Okay? So, but just imagine, here are some even higher quality images from the planet data. I mean, look at this image, and look, this is for different months, or different weeks within the same year. And they're asked to distinguish among, in some cases, more than 20 classes. Imagine how difficult that is. So they have the 85,000 points. Each point is one of these many classes. So this is an enormous data set. And they need to compare that data set to the Mapbiomas time series. And then the first big challenge is, well, what metrics are you going to use to compare these enormous data sets? So the first thing that they did is to assess the agreement at each time point. So here are the time points from 1985 to about 2022. And I encourage them to focus on the disagreement rather than the agreement. So this is the total disagreement about, in 1985, about 13%. But notice that most of it is the allocation disagreement, and a small proportion of it is a quantity disagreement. Each year they update their data. This is for collection 7. Each year when they update their data, they increase the collection number. And this is for the level 2 classes. There's about 20 level 2 classes. So level 2 are more detailed than the level 1 classes. If you look at the level 1 classes, well, there's only 5 level 1 classes. The errors drop because at the level 2, if you're trying to split the difference between 2 very detailed classes, maybe they're both agriculture, well, you got it right as agriculture. So the error rates drop. And so the error rates now are better than they were previously. So this was from a previous collection where the error rates are higher. So over time, they're making their data agree more with the reference data, which is a great idea if you actually believe the undergraduates who made their decisions under the supervision of LePeag supervisors. You know, if all the reference data is perfectly true, then it's a good idea to make your maps match the reference data. But think of the process to create the reference data. It's a really challenging job. Furthermore, after years of doing that assessment, when the Scientific Advisory Committee met last year, they said, well, the entire purpose of the Mapbiomas time series is to say something about the change through time. But that error assessment was only about the accuracy at the time points. What we want to know is a different question. We want to know how accurate do the data portray change. And so the more I thought about it, I realized that the error at time points is really not helpful to understand the error of change. Think of it this way. If the reference data agree with the map for 90% of the spatial extent at the time points, and change occurs on less than 10% of the extent during each time interval. So the time interval is the difference between the 2 time points. It's possible that if the maps are 90% correct, it's possible that all the change is mapped perfectly. It's also possible that all the change is mapped wrong. Because with this 90%, that means it's 10% wrong. If where it's wrong is where it's changed, it could be that all of the change is wrong. So even when the maps are 90% correct, that tells me nothing about how accurately the maps portray change. So we really need specific measurements to measure the data quality during the time intervals, rather than measuring the data quality at the time points. Okay, so we return to this exact same Venn diagram, where last time when I was showing this, the Venn diagram was related to time points. Now we're going to have the same Venn diagram, but we're going to relate it to a time interval. So rather than have the presence at a time point, we're going to have the change, the circle is going to show the change during a time interval. Okay, so for a time interval, one circle, the red circle is change on the map, the blue circle is change according to the reference data, and we have the same words, hit, stable, and hit where it's an intersection. But we can also have, when we have multiple categories, we might have a place where the map says change, the reference data say change, but they disagree on which classes are changing to which. So that's what we call a wrong hit. We can also have wrong stable. It could be that both the maps and the reference data show that the land is stable with the same class, but it might have the wrong class. The map might say stable forest, and it might actually be stable agriculture. Okay, so with these concepts, I worked with Ana Paula Matos at LePig, who's doing she was a supervisor during the creation of the data, and now she's doing her doctorate to analyze these 85,000 points. So when I first arrived in Brazil about a month ago, I was working with her, and I said, well, the first thing I want to know is on what percent of Brazil did the interpreters disagree in a way that would cause disagreement during the time interval. So if for each time interval, you have 2 time points, and you have 3 people evaluating the first time point and 3 people evaluating the second time point. So the only way they all 6 of them agree is if all agree on the first time point and the second time point. So there's lots of ways that they can disagree concerning what's happening during an interval. And so we have annual time intervals here, and the height of the bar is where there's at least some disagreement among the interpreters. So we're having on average, about 27% of Brazil, the interpreters do not agree with each other completely during time intervals. 27% of Brazil. Well, how much of Brazil changes per year? Like less than 1%. So you have 27 times more disagreement among the interpreters than you have change in Brazil. So, I don't know if I want to call this reference data truth. That's one big take-home message. Also, I saw this. I asked Ana Paula, well, why do we have so much no data at the start of the time interval and at the end of the time interval? And she said, well, the reason is clowns. I'm like, clowns? Yeah, she said, clowns in the air. And I said, do you mean clouds? She goes, oh, yeah, clouds. Okay. And I go, but what? Were there more clouds at the beginning and the end? She goes, no. The instructions to the interpreters, they're looking at a time series, and Brazil has a lot of clouds. And so if they see forest, 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 cloud, 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 forest, they just say, well, I assume under those clouds were forest, and they call it all forest. And so actually, if they honestly sled clouds, you'd probably have cloud cover on, more than 5% of Brazil across the entire time series. So you have 5 times more cloud cover than you have change on the ground. How are you going to believe that your maps are accurately showing change? It's really challenging. Another thing we looked at is whether or not there's more alternation in the maps than there is in the reference data. So alternation is a type of change where the same places are changing again and again and again through the time series. And so we did this analysis for the level 1 classes, the level 2 classes, and the level 3 classes. The reference is the reference data, and this is the maps. So at the level 1 classes, this the not alternation component, that's the sum of the quantity and allocation components. But what we see is a much larger alternation component, but even regardless of what we do, what we assume about the node data, the main reason why the maps show more change than the reference data is the maps show more alternation. Okay, so we're finally figuring out the patterns that explain the main differences between the Mapbiomas time series and the reference data. If you look at the class level, this is the coarsest class level, then more detailed classes and more detailed classes. So, and this concerns the annual change. This is up as a percent of Brazil. So, according to the map, the change is the union of misses, wrong hits, and correct hits. So, the blue, the red, and the green, that's the change according to the maps. The change, that's the change according to the reference data. The change according to the maps is the red, green, and yellow. So there's much more change in the maps, there's many more false alarms than there are misses. So if you believe the reference data, then the Mapbiomas time series is estimating about 4 times more change than what the reference data show. And that's true regardless of what class level you consider. So here we have that broken down by year. Again, you see about 4 times more false alarms than misses. But if you consider the no data, look, you have more no data than you have change in the maps. Okay? But if we zoom in on this particular graphic, again, we see, well, I've been talking about the disagreement. Do the Mapbiomas maps agree at all with the reference data? Well, on some patterns, yes, they do. Both the reference data, the reference data, the amount of change is the top of the green. And notice how it's decelerating. The Mapbiomas maps also show deceleration. Okay? Well, at least they agree with each other in some respect on that one. We had this broken down for all of Brazil and by biome. So this is showing for all of Brazil, the errors are the false alarms, the wrong hits, and the misses. And the red is correct hits. So there's 36 times more error than correct hits for all of Brazil. Holy smoke. But that varies by biome. Holy smokes, look at the Pantanal. Okay, well, for those of you who know the Pantanal, it's a very, very difficult biome to map. It's so remarkably dynamic. So it's important to be able to characterize these differences because each year Mapbiomas, revises the maps. They have to know how to revise them. You have to know where the disagreement is in order to fix them. We've been looking at the change, but if you look at what's stable, wow, you see even more disagreement on what's stable. Okay, so here, when I have wrong stable, that means that both the map and the reference data show stable, but they disagree on which class is stable. So it seems we should also be concerned with, the errors of the stable class are multiple times larger than the errors of change. Okay, now on to the last part of the presentation that focuses on soybean cultivation in the Western Cerrado. This is where NASA has funded my research project. So we have this rectangular area in the Western Cerrado, which contains the 9 municipalities in the Western Cerrado where most of the soy cultivation is in Western Cerrado. Now we have these maps of each year for 33 years where each map shows either the presence or absence of soy. And we overlaid all those maps to make this map where the scale goes from 0 to 37 because we have 37 time points. and the darker the red, is the more number of years of presence of soy. On the right-hand side, the scale goes from 0 to 36. This is the number of changes in soy, which you can, it's difficult to see, but even if you were to see that, it seems what you want is some combination of this type of information to get very helpful insights. Furthermore, that rectangle there, that rectangle of the region was drawn for convenience. And we just wanted to capture the region that had soy. But it seems it'd be silly to give the results as a percent of that rectangle, because that rectangle is arbitrary. So we defined a region that we called the unified region, and that's the region that has at least 1 year of soy. So we can present the results in terms of percentages of the size of soy. Then, after overlaying those maps, we made these trajectories. So each pixel here is one of these 1, 2, 3, 4, 5, 6, 7, 8 trajectories. The main one you see is the dark blue. That's gain without alternation. So that's through the time series. It starts as absence, it gains once, and then it remains presence of soy until the end. The next color you see is gain with alternation. So that means it starts as absence, it gains, and then loses gains, loses gains, loses gains, loses gains. It alternates and finally ends in presence. We see some yellow here. The yellow is its all alternation. It might start as absence, it gains, loses, gains, loses, gains, loses. So it starts and ends as absence, but it alternates through there. So we took those concepts of those trajectories and we made this graphic as time goes from left to right for these time intervals. We have gains going up from the time axis and losses going down from the time axis. So the height of the bar here is the size of the gain during that time interval. And the depth of the bar is the size of loss during that interval. And each bar is segmented according to how much of the bar comes from each of the trajectories. So we can see, so the dark blue is essentially permanent soy. And so we can see when that permanent soy was started. We can also coarsen the temporal resolution. Here's the analysis at 1 year temporal resolution. We can coarsen that to a 2-year temporal resolution, in which case, if you have alternation happening in consecutive years, then if you look at these alternate years, then that change disappears. So the allocation change in that one drops. And we can make those temporal resolutions coarser and coarser until the final temporal resolution is the 32-year time interval. And so at each time interval, we can compute the overall change and compute it in terms of the 3 components of a quantity. This is a net gain, a tiny exchange. Exchange is where from the very beginning to the end of the time series, you have gain in some places and a loss in some other places. But the main component of change here is alternation, where the soy, it's soy and then it's not soy, and then it's soy and then it's not soy. And when I first saw this, it was quite shocking. And even some people who are agricultural experts said, wow, that's pretty interesting. I didn't necessarily expect that. So if you're interested in more of these or to how to make these computations, you can get my book. If you don't like the price that you see from the publisher, I've heard you can get it on Amazon for about a quarter of the price. Or if you write to me and ask me very nicely, well, you might get a response. So here are the main points again. We created novel methods to compare the Mapbiomas time series of land cover change to reference data that derive from visual interpretation. The Mapbiomas data show more alternation change than the reference data show, about 4 times more. Uncertainty in the reference data is 30 times larger than the annual change in the Mapbiomas data. And we show a novel methods to analyze change of soy in Western Bahia. And I just submitted that fourth one. I just submitted a conference proceeding at Space Week that will be happening in 2 weeks in Fortaleza. And so you'll be able to find that conference proceeding soon at that website. Obrigado.
So, thanks so much for your presentation, Professor Pontius. I would like to ask for the moderators to get their place. Professor Pontius, please have a seat. Now it's time for us to discuss a bit about we have delighted with this presentation. And then I would like to open the question for the audience, which we have over here or even online. You can, the guys that are online, just to write down the questions, and we are going to make to the moderators to receive these questions and ask and talk with Professor Pontius. Yep. Meanwhile, the moderators, it's with you, yours, the job. Thank you.
Good afternoon, everybody. Thank you very much, Professor Pontius, for your talk. I really appreciate your positions, your propositions as well. I prefer reference data instead of ground truth because they have quality as well. And I was just thinking about loss and gain could be commissions and omission errors, yeah? Okay, that's good.
Well, right, so yes, so at the beginning I was with the Venn diagram. We had if you're analyzing change, the type of disagreement can be loss and gain, and when you do quality assessment, the words I use were miss and false alarm. Those misses are exclusion errors, and the false alarm are inclusion errors.
Inclusive.
Right.
Yeah.
Or inclusion, also known as commission errors.
Commission.
Right.
Okay, that's good. And you know that most of the index coefficient, like kappa, that you written about, and overall accuracy, they are non-spatial statistics.
Right.
And do you have any idea how to represent the spatial reliability of the data?
Well, I think the best, that's why we make maps. Maps show where it is. Yeah. My advisor gave me so many wonderful pieces of advice. He said, the first thing you do when you when you do analysis is get the data, plot it, and look at it. Get the data, map it, and look at it. You know, we can process it with a neural net, the organic neural net that's on top of our shoulders. That's probably the first thing we should do. There are there's many metrics that measure very particular patterns. But our eyes and mind can immediately see patterns for which it can be very tricky to design a particular metric. That question came up when, even with the Mapbiomas data, we wanted to get some idea of where the errors were spatially. So that's why in one of the slides I presented the results by biome. And so that gives, where we saw, the disagreement in the Pantanal was many times more than in the Amazon. Well, in the Amazon, I mean, you call it forest and you're probably going to be right.
Yeah. have you considered the possibility, because you have 8,000
85,000. And the distance between what and what? That's a very interesting question that I've been thinking about for years. That that type of question relates to the allocation difference, where you have omission of a class in some places and commission of the same class in other places. And the question is, how far away are the omissions from the commissions? Because if if you do an analysis at the pixel level, if you have two pixels that are side by side, and one's a commission error and the other is an omission error, you get penalized for two errors when they're right next to each other. You know, your maps might be misregistered by 4 pixels. And so it seems ridiculous to have penalized for so much allocation error that's over very short distances. But if your omissions are very far away from commissions of the same class, well, then that's a serious allocation error. And so it seems we should have a larger penalty for that. So one way that I get at that is doing a multiple resolution analysis, where my philosophy is that, you know, these 30-meter pixels, they're 30-meter pixels based on convenience in the available technology at various points in history. You know, the electrical engineers that made the sensors that they put it on satellites could map at 30-meter pixels. That doesn't mean we should feel obligated to make maps at 30-meter resolution. That 30-meter resolution is just a matter of convenience. So we shouldn't look at the errors exclusively at that resolution. So what I do, I perform these metrics at multiple coarser resolutions, and then what happens, the errors tend to shrink at those coarser resolutions. Just as I presented the disagreement at the fine temporal resolution, but at the coarser temporal resolution, then the disagreement shrank. You see the same thing, that that allocation disagreement will shrink as you go to coarser spatial resolutions.
And the last one, how is the impact of the registration in your analysis?
Okay, so the question is, how big is the impact of the image misregistration? So, and I'll just explain the issue a bit for people who might not exactly understand. You know, we have these satellites flying over, you know, doing laps around the planet in orbits, and each time they fly over, they do a scan. But if you want to know the temporal change, you have to overlay those images. And it can be very tricky to have them overlaid exactly. So if they're misregistered, it means the images are maybe the same rows and columns of pixels are showing slightly different places on the ground. And I think it can be a serious issue. And I've had projects where it's a serious issue. My colleagues told me, oh, Gil, we're going to, apply for grant money and we're going to make really accurate maps. And I said, how accurate? And they said, they're going to be half-meter resolution. And I said, half-meter resolution is not a measurement of accuracy. I asked about the accuracy, not about the spatial resolution. What I found is if you have very precise spatial resolution, then you're just going to have a lot of pixels, and it means you're going to have to spend a lot of your budget on computers to store the large files. So I've had 2 maps that were half-meter resolution, the time difference of a few years, and I started analyzing the temporal difference, and I saw these parallel lines on the landscape, and I'm like, what are those? And I was like, oh, those are ditches, but there was only one ditch on the landscape, okay? But the images were misregistered by just a couple meters. Well, if it's just a couple meters and you have half-meter resolution pixels, you're going to see a lot of differences due to just misregistration. So that's another thing that the allocation difference will be able to make those types of differences disappear. So sometimes when you go to this multiple coarser spatial resolutions, that can also make those allocation errors disappear.
Thank you very much.
That's a solution. We will exchange. That's an allocation change.
Nice. Well, thank you actually for the lectures. I have received actually a question in WhatsApp from Dorothea. She is actually a lecturer in Tanzania.
Oh.
And she wrote here that she's making in a national park, collecting field data samples and also different biophysical parameters. So in those field sample plots, there is a lot of work needed to recognize the species and measure the height and the diameter, the braided height and other parameters as well. And sometimes it really takes more than one day to make a single plot or to finalize that. But this is a work that she cannot perform using high spatial resolution images only. She needs actually those measurements to really be certain that this location is really that type of forest, because it really takes account the number of species and other biophysical parameters. So it's not possible to make or truly base, let's say, on visual interpretation and source images. So we really have to go in the field. And her question is actually how many samples are needed to make a good assessment?
Well, first of all, I'll say karibu wa Tanzania. I lived for 2 years in Morogoro, Tanzania. So I send my messages to my good Tanzanian friends. Well, that's an excellent question, and I hope you're asking it early on in the process before you've invested too much time into field work, because field work is extremely costly in terms of time, money, and mosquito bites. And you don't want to get to the end of the analysis and say, oh, I wish I would have, spent 2 more days in the field and my results would have been, much more interesting. So my short piece of advice is get the advice of a professional statistician. There is an entire science of sampling, which is absolutely crucial when you're designing your research study. And the number of samples you need depends on several factors. It depends on how complicated the thing that you're sampling, how much variation there is at your sampling. It also depends on how narrow you want your confidence intervals to be when you get to the end of your analysis. And it depends on how strong of a signal you want to detect. And so it's non-trivial. And I did a master's degree in applied statistics. and an optional course was sampling. And when I was a student, I thought, why would I want to take an entire course on sampling? Well, are we going to just talk about different random number generators? And because every single one of my exercises in my master's degree in statistics, it began with the statement, assume a simple random sample. But it wasn't until, so I did not take the sampling course. But my first job after my master's degree was working for the Department of Agriculture designing their non-random sample. And so I had to go back to school to learn all of this. And it's very important. If you don't have a intelligently designed sample, you're going to have a very poor use of effort. And so work with a statistician to get advice, but here's some general principles. You want to make sure that when you sample, you know the probability of every element in your population of inclusion in the sample. That doesn't mean that every piece of ground has to have the same probability of inclusion, but you have to have a known probability of inclusion. And you also want to sample with more observations in those places where you're most uncertain. And so really, you want to put more samples in the places where you think you're going to be wrong, because that's where you're going to get your most helpful information. But then at the end, if you've had an intelligently designed, stratified design, you can make an unbiased estimate for your entire region. So get advice on how to do stratified random sampling I would think, is my first recommendation for our friend in Tanzania. And this is such an important issue. Really, it's for anyone that's going to invest tedious time to collect data.
Great. I also would like to share a personal experience during my master degree and performing a vegetation map, taking into account different or the variability of the physiognomies that occur in Cerrado. And this was exactly a region, a transition region from Cerrado and Caatinga. So the seasonal influence is quite big. So we performed our field work during the rainy season. So, and then we come up with 5 major land cover types, let's say vegetation types, physiognomies. And by looking in a time series in a given year, we see that there is a lot of changes that occur in vegetation. And then we performed a second field work. And then we realized that, okay, the vegetation looks different. It seems that is even deforested, but it's not. It's just because of the leaves that falls in the ground, so it becomes brown. And when you look for optical images, is really another spectral signature, so it really looks different. So, and then we come up with another set of classes and physiognomies and perform everything from zero. So the question is, how important is actually to know a given region and not to only take as a true single image to be something representative in a given year. I'm talking this or asking about that because if you think in this environment, when we look for a larger area, so you need different images to make a mosaic. So how to handle actually with such seasonal changes and then to perform a good accuracy assessment? It's actually a bit tricky, but I would like to hear your experience.
Well, I think you explained several reasons why it is really, really difficult to make a time series of maps where you can say with certainty that the differences between the time points indicates somehow true change on the ground. And I before I got into this field, I did not appreciate how difficult it is to make a time series of maps. Because it seems, well, you describe one region of the world that has a lot of seasonality. You know, almost everywhere in the world, there is more variation within a single year than there is across decades. And well, you can think there's also, visually, there's even more variation from night to day. I work on a coastal region where we have tides coming in and out twice a day. And the level of tide is multiple times more than even the change that you would get through big storms coming through. And then we're trying to detect sea level rise, and that's a tiny portion compared to the tide or storms coming through. So I think it's a very common problem. And you certainly need to integrate what you know qualitatively about the landscape. And I think you have to define very clearly about exactly what types of change you want to measure. And where I'm from, in about a latitude about 42 degrees north, the seasonality, we have such deciduous trees, the image will look completely different if the leaves are on or if the leaves are off. And so the tradition at that latitude is that organizations will take their images in leaf off. So that's, like around April. But it's really, I think from personal experience, there's a lot of complications. And I have, there's no one straightforward answer because there's so many issues.
Great. We have actually one question from the audience that is actually online.
Yeah.
And the first one is from Marcos Cardoso. He acknowledged actually the lecture. And he's saying that he is part of Mapbiomas solo initiative. And his comment is, usage and coverage is one of the key dynamic variables along with other indices. We use it. And I would like to ask how you recommend handling these class transitions.
I don't know if Marcos is talking about the difference between the use and the cover,
Oh, okay.
because remote sense give you
Cover.
the cover,
Right.
not the use.
Right.
And maybe that is the difficulty
Okay.
here to measure and so on.
Well, I guess that relates to what you said about knowing qualitatively your landscape. And for the people new, the land cover is what is physically on the surface of the land. It's what a sensor that's on an airplane or a satellite can see. The use is how humans are using that land. So you could have forest that's being used for watershed protection or for recreation or for hunting or for timber production. And, well, I guess with every research question, you know, you need to define specifically exactly what you mean. And gosh, you know, that sounds so obvious, but I think most projects, they start out with a research question that they think is precise, but then when they start to do the research, they realize, oh, I think we need to revise this. You know, so they might say, oh, I want an accurate map of land cover. And then they say, well, but I want to know about farming. Well, farming's not a land cover. Well, that's a land use. And then, you know, what type of farming? And then the question gets revised through time. So I guess one piece of advice that relates to this, I don't know if I'm answering his question precisely, but when I was told in 8th grade the way science works, you have a hypothesis, you go out and collect data, you give evidence for or against that hypothesis, and you make a conclusion, right? Then I get into the profession. That has nothing to do with the way practical scientists do. You know, the first thing they do is go to the funding agency and see what someone's willing to pay for, and then write a proposal that they think these people will be interested in. And then if they get the proposal, they start doing the research, and then they realize their research question, they're never going to be able to solve it, and so they modify the research question. And, you know, there can be learning that can happen that way. So that's what comes to mind when I heard what Marcos said. I don't know, if Marcos, if I answered it, maybe you can type in more whether or not that addresses your question.
And most of Mapbiomas, they use pixel by pixel approach. What about to thinking about object approach, how to assess and use your method in order to assess the accuracy?
That's a very interesting question. So, and I'll just summarize for maybe someone, people who are not familiar with what objects are. So if you think of a satellite image, it has rows and columns of pixels. But an object would be a collection of pixels. So like an agricultural field, like maybe agricultural pivot, it'd be a collection of pixels that form a circle. And so some classification procedures use the information about the pixel and its neighbors to then classify an entire an object, collections of those. And, you know, that type of classification certainly had some obvious advantages. I'm constantly wondering about how to assess the accuracy based on this object, on these objects. And from some of the literature I've seen, people just revert to pixel level accuracy assessment. And it's like, well, you're sort of defeating the purpose of what you're trying to do in your methodology. So I was curious about this, and I worked with my students. So I had 2 doctoral students to work on this, and we reviewed the literature. We reviewed 100 journal articles that performed object-based image analysis. And we submitted this to a journal as a review article. And the reviewer said, only 100 papers? You need 200 papers. So we went out and got another 100 papers. And what we found is no magical method to really do the accuracy assessment. I mean, but some of the papers, as I read them, they didn't even make sense, because they said, well, we took each object in our classification and each object that someone digitized by hand and compared one object to the next. But the number of objects they had in their map was not even the same as the number of objects in the image. So I don't even know how they made a one-to-one correspondence of which object corresponds to which. And even if there is the same number of objects, you might have one region of the map that's segmented a lot more than another region, and I don't even know how to create a one-to-one correspondence between the objects. So I think for people reading the literature, if you read a journal article and you think, well, I cannot understand this, there's a decent chance that it's just poorly written. It's not you, And so, but I don't know any crystal clear, obvious way to do map comparison when you have these objects.
Any questions? Okay. You need to comment on. Introduce yourself. Yes, please. Introduce.
Hi, my name is Edson. I'm a PhD student here at UDESC. And thanks for the lecture, Prof. Gil. I have a question in terms of how can we bridge the gap between science, specifically on geographic and all the data, versus the politics, right? So for politics or policymakers, when you mention about the 27% error, they will say, hey, I cannot trust on this. I understand that science is based on really strong data, making sure that we have the right approach, but many times that can be perceived as not trustful data. So how can we bridge the gap and make sure that when we address this and when we voice our research findings, how can we make sure that we are not get lost in terms of how to translate that for especially policymakers?
Yeah, that's an excellent question. Well, I think the world had an interesting experience with all of this through COVID, and in various countries we had experiences when scientists would express themselves in a particular way, and we saw a full range of political responses, from very intelligent to just downright embarrassing. So it's very difficult to predict what a political response will be. But I think if scientists give the impression that we're hiding anything, it's going to hurt. So I think we need to be open and honest. And I think it's easy for scientists to make the mistake that they think no one will listen unless we portray ourselves as confident. And especially experienced politicians, they're always making decisions under uncertainty. Some major decisions, whether or not to go to war. Well, we have this information and we don't know even not to believe it, but they still make a decision. Every decision is made with uncertain information. So I think it would be for scientists to have a big mistake by trying to hide the uncertainty, because it'll come out eventually. And if scientists present their, even their predictions as so certain, well, what happens when they don't come true? We've just lost credibility the next time around. So I think all of us have experience with making decision under uncertainty, even in geographic things. I mean, we hear a weather forecast every day. And through repeated experience with a weather forecast, we realize, okay, I can probably trust it for today, and I'm not going to trust it for next week. But if I want to know what it's going to be next week, I'll wait a few days. And so I think, people are used to deal with uncertainty. And I think scientists get ourselves in hot water when we think that in order to be effective, we must present with great confidence and high levels of uncertainty, because that will ultimately, when next year when we do another analysis and the number's different, we can say, if we gave it error bounds in the first year, we can say, look, it's within those same error bounds. But so I think all of us are going to get into trouble if we start to hide anything.
People are asking if your presentation will be available for them.
I think the video, I've been told that the video will be available online.
Oh, yes.
And
Through the video. Yeah.
yes.
Okay,
Very good.
good. Any questions? I will invite Professor Francisco to close the section, and we would like to thank you, Professor Pontius. Oh, you have one?
There we go.
Let me make one question more. Well, I think the students are a bit shy and don't want to ask, but given the last decade, we have several satellites being launched, and we have also a perspective of having even more in the forthcoming years. And they are not only optical sensors, but also hyperspectral. We have actually from Nmap, Prisma, even the planet constellation is also considering to have those sensors, but also from radar. So what you could suggest them for future research about perspectives and using multiple satellite data and considering also the challenges involved and data accuracy assessment. If they work with different types of data, how to come in a common, let's say, way when you do data accuracy assessment.
Well, I guess overall, especially for the students, Jess, you are in a wonderful field. If you're in this remote sensing and GIS, every year I'm just amazed by the advancements in the technology, and it just makes it fun. I mean, it just is really constantly interesting, and the technology is just going to keep on getting better. And so, but with every new technology, there's going to be new challenges. I mean, when I was coming up through the ranks, one thing has been consistent over the last decades. Everyone claims that they're using high resolution imagery, but just as the decades go by, the definition of what they mean changes. When I was, a graduate student, the 30-meter Landsat resolution, that was amazing. That's high resolution. And then it was half meter, and now it's 6 centimeter. And when I was dealing with Landsat, they said, well, the problem with Landsat, they said Landsat was going to solve the problem of the previous generation that had 5 kilometer resolution. And at 5 kilometer, you can't see the you get mixed pixels. Of forest and agriculture and urban. But then I started working on a half-meter resolution. Well, you also get mixed pixels, right? You have, the side of the road and grass, within a half meter of each other. So, and also when we had finer resolution, we had half-meter resolution pixels, and one of our classes was water. Well, after it rains, there were puddles larger than a half meter by a half meter. And, so I'm not sure if we really wanted to be measuring whether or not it rained within the past few hours when we had that water category. So I would say, every type of technology. Technology is complicated and expensive to build. People build it for very particular purposes to solve particular problems. But for each problem it solves, there's new challenges. So I would say it's a constant struggle to figure out how to design a metric for your particular research question. It might sound like, well, it is the obvious thing to do, to have a metric to answer your research question. But how exactly to design that metric can be really tricky. But chances are, what you've seen traditionally in the literature is not going to be, in the past, is not going to be a good match for your particular research question, for your particular project. So that's an opportunity to be creative.
In this context, just to finalize, well, nowadays we have bunch of scripts and codes and machine learning methods, and so if they have actually satellite images from different sensors, or choosing one particular sensor and using actually these data sets, so you start actually to generate maps using approach A, and then approach B, and then approach C. So it means the traditional machine learning methods coming up to deep learning methods. So one takes actually 50 minutes, the approach A. The approach B takes actually 2 hours, and the approach C takes actually 2 days. So how to actually apply a test and say that, okay, these 2 or 3% that I have in gain and accuracy is in fact worth to be used. Should I rely on approach A, or should I really go for approach C?
Well, that's an excellent question, because many scientists are faced with that exact situation. And it's a general question of how do you decide what model to use? Even with people who might not be doing specifically remote sensing. But, should I take this approach, that approach, or some other approach? So I'm not here to recommend any particular algorithm. But I have a paper coming out in the Annals of the Association of American Geographers just this month that addresses this issue with concerning model selection, and we urge readers to ask themselves 4 questions when you decide what model to choose. First question, can you understand the model? Second question, can your audience understand the model? Third question, can you control the model? Fourth question, is the model relevant to your research question? And most projects with which I'm familiar, the answer is no to at least one of those questions. And especially even question number 1, can you understand the model? And if you cannot, do not assume that it's your fault, that you're somehow not intelligent. No, if the documentation is poor, then there's no way you can understand the model. And it requires tremendous skill and dedication on the part of software developers to create good documentation. And many models that I know, good documentation just does not exist. And so I don't care if that model's for one particular case study gives you, a few points higher in some accuracy metric. If you don't know why, then you probably haven't learned anything. Well, one of my good colleagues, Professor Dan Brown at University of Washington, said that when I agree with him on this point, it's one of the main purposes of the model is to learn something. Not necessarily to, predict the future, or, for this particular case study, make this particular type of map. And so if you have a procedure where you're not learning anything, then you've got to question the value of that particular model, I guess is another question that I would urge users to ask themselves. Am I learning anything from this particular model?
Great.
Well, it's 5 p.m. Then, in the name of UDESC University and also Geography Department, GeoLab, the Lab of Geoprocessing, and also our post-graduation course, which is territorial planning and social environmental development. I would like to thank you very much for your presentation. It was an excellent discussion, and also to our moderators. Also, I would like to thank our audience and our online audience. And it was a great honor and pleasure to receive you over here with your expertise and your knowledge. It was really a good experience to have all of your lecture and your expertise about the theme. I wish you all the best. You are stay here in Brazil, whatever you need. We are your partner. And also, I would like to thank you for Mapbiomas group and our partners that work together with us here in Florianopolis. And I wish all of you really rest of the day. Thank you so much.
Thank you.